This presentation will be on fundamentals of harmonics, which falls under the power quality analysis modules. Let's briefly go over the definition of what harmonics are. The presence of harmonics in electrical systems means that current and voltage are distorted and deviate from sinusoidal waveforms. They're typically present, they're represented by a wave having a frequency that is an integral multiple of the fundamental frequency. Harmonic currents are caused by nonlinear loads, mainly, connected to your power system. Let's talk about why harmonics are harmful. The harmonics overlay themselves on the fundamental waveform, distorting it and changing its magnitude. As you could see from the illustration, on the left hand side you have your fundamental frequency and the voltage sinusoidal wave, and you also have the third harmonic. When you combine the two on the right hand side, you could see the superimposed or overlaid output. Let's continue on why the harmonic distortions are harmful. First of all, let's go over high current distortion and what kind of problems they cause, and then we'll get into the high voltage distortion. So for high current, mainly it'll increase the eddy current losses in transformer and generators. It'll also increase current through resistance losses in conductors, transformers, and generator windings. We could also overload neutrals. Now let's take a look why high background voltage distortion, or the total harmonic distortion voltage, causes problems. First of all, it could cause failures of switch mode power supplies on PLCs, computer, and instruments. So if you have any of these problems, a lot of times they could be attributed voltage harmonic distortion problems. If you have PLCs that are currently, or power supplies that are currently burning up, it may be a good idea to perform a harmonics study for your system. Also, generator AVR, your auto voltage regulator, it could malfunction if there's serious voltage distortions in the system. It can cause also false reading on critical sensors and instrumentation. Increase operating temperature on induction motor winding and rotor bars, leading to premature motor failures. Now let's briefly go over what causes harmonics. And as I mentioned earlier, it's because of non-linear loads. And just as a brief description, a non-linear load is one that draws current in a non-sinusoidal fashion, even when the voltage is a perfect sine wave. So for example, over on the right hand side we have an illustration where we have the voltage sinusoidal wave, and then on the bottom, because of the chopping that happens in power electronics, you have the current, the distorted current. Nonlinear loads typically would include our static power converters, pulse width modulated drives or PWMs, switch mode power supplies, very similar to what we would have in our DC power electronics, for example. Inverters, very common now with solar PV and some of the renewable inverters that are being installed for solar farms. Arc furnaces for heavy industry. Of course, variable speed drives, which are found, in offshore platforms, as well as in most industrial sites, and even fluorescent lights. These are some of the causes that would be considered nonlinear loads. What I'd like to do briefly is just kind of give a brief introduction to the IEEE 519 standard. Then we'll get into some of the differences between the 1992 519 standard and the 519 2014 revision. So the IEEE 519 can be used as a starting point. It's in essence a guideline to be used by engineers for power system design consideration. And acceptable harmonic content limits for individual equipment should be obtained from manufacturer. So really the 519 concerns with the harmonic distortion that you introduce into the grid at the point of common coupling, or PCC. So if you are concerned with harmonic contents inside your site, you can certainly use the 519 limits. However, it's a little bit out of the scope of work, but we'll go over an example on how to apply it using software. And but if of main concern is the individual equipment harmonic limits, it's a good idea to always start with the manufacturer. Okay, so let's quickly jump into what are some of the differences between the IEEE 519 1992 versus the 2014. Just so everyone is aware, for the IEEE 519 1992 is what currently is implemented in software like ETAP. In the next update of ETAP, the IEEE 519 2014 will be released. Let's start with the limits for total demand distortion. This was the old table 10-3 in the 1992 standard. And on the IEEE 519, the new 2014, it's equivalent to table number 2. It remains the same, so nothing has changed here. As you could see, what this table is really telling us, right, is the total demand distortion column that's over on the right hand side. Basically what that represents is whenever we have a SCR, or short circuit ratio, which is the maximum short circuit current at the point of common coupling, over the maximum load demand current of fundamental frequency, again at the point of common coupling, or PCC, right? We get the short circuit ratio, which is what you see on the first column on each one of these tables. Typically, an SCR, or a short circuit rating, under 20, let's say 10, typically expresses a very large load. An SCR that is greater than 1,000, for example, typically represents very small loads. And in essence, what this means is that for a weak power source, so a utility that is very weak with large demand current relative to the rated current, will show greater waveform distortion. On the other hand, a very stiff power source, or large short circuit contribution, operating at a low demand current, will show a decreased waveform distortion. So what that typically means is the higher the available fault at the point of interconnection, or PCC, right? The decreased waveform, you'll see a decreased waveform basically. Continuing with some of the significant changes between the 1992 and the 2014 standard is the following. Over on the right hand side, we have table 10-2. That's from the old IEEE 519 1992. You notice we had a voltage range from 120 volts to 69 kV, which called for a total harmonic distortion voltage of 3% for special applications, and 5% for general systems, with a 10% allowed for dedicated systems. Over on the left hand side, for table number 1, that is from the IEEE 519 2014, we now have special bus voltage range that has been added. So now we have a new limit for buses under 1 kV. The individual is 5%, and the total harmonic distortion is 8%. So that's a significant change. And for bus voltages above 1 kV and up to 69 kV, the total harmonic distortion voltage is still remains the same. Individual is at 3%, and the total harmonic distortion total is 5%. So that didn't really change. So the main impact you would have is if your facility, right, or the mainly commercial buildings, for example, that have an incoming at the point of common coupling that is under 1 kV, right? You now have an increased allowable total harmonic distortion voltage, which increased from 3% to 5%. Okay, moving now over to the and here's just another representation here of the voltage distortion limits. These now have been built into the new version of ETAP. So you'll be able to have a harmonics rulebook that contains these new voltages that you would be able to apply not just at the point of common coupling, but if you like, you would have different global settings or specifically at individual locations. The IEC 61000-3-6 has also been updated. Just so everyone is aware, the new update has also been added into the ETAP, the new ETAP harmonics rulebook, and we'll go over that here in a brief example. Before we go over harmonic sources and software modeling, I like to go over the where the new rulebook is found. So let me bring up my copy of ETAP here. I'm running harmonic analysis mode. Again, the new version of ETAP complies with the new IEEE 519/2014. The new rulebook allows the user to customize. So under the rules pull-down menu, I go over to harmonics. As you could see, for those of you who perform consulting services, you can now have multiple limits based on the harmonic standard that you will be applying. As an example, what I have here is 3 rulebook, the IEEE 519/2014, which is what we use in North America. I also have the British standard, which is the G5 4-1, and I also have the IEC 61000-3-6 2008, which is typically used in overseas in Europe. If we briefly go over into the how the rulebook is put together, right? We could see here the new current harmonic limits, right? And voltage harmonic limits. You can now then apply. Let me close this. You could actually, if I look at the point of common coupling, my incoming bus here, and if I go over to the harmonics tab, you notice that you now have new options. You could perform a global compliance based on the rules in the rulebook, as described by us in the standard. You can also perform a local compliance rule where you can actually select a rule book for this particular location, and you can even look at you could even launch the limits from here, or launch the rule book from here. Or if for those of you who are opening existing harmonic analysis projects from previous versions of ETAP, it'll typically be set to the old IEEE 519/1992 option, where you used to specify the total harmonic distortion limits, both voltage and current, directly in the bus. Okay. Also taking into account now is your short circuit current, as we mentioned earlier, right? Your short circuit ratio will have an impact on the waveform distortion. So now you can either select calculate it and allow the short circuit study engine perform that for you, or you could specify user define if you happen to have a recent enough study and you want to use that value. The other item that has been enhanced for 2014 is the transmission line cable model as well as the skin effect model for transformers, synchronous motors, induction machines. For transmission line model, you now have the ability to use the short line model as well as the long line model, and you get to specify when the long line model or cable begins. Let's go back into the presentation here, because what I like to do is I like to briefly go over just an exercise on how to model a harmonic source, whether it's provided to you by the manufacturer or perhaps you may have captured the harmonic source using a meter. You go out in the field, you measure it, or perhaps you're trying to model a variable speed drive from a given manufacturer and they've provided you with the harmonic source. What we're looking here is a typical current spectrum for a 6-pulse drive. You'll notice on the right hand side we have our magnitude. So this particular drive has predominant harmonics on the 5th and the 7th. The very first bar that you see on the left hand side, that is your fundamental current, and that would typically be the full load amps rating on the drive or on the device. What I'd like to do now is jump into the software and show you how you can model a typical or a manufacturer provided harmonic source. What we have here is just a small industrial system, and right in this location down here you have a composite network that contains some DC sources and loads, and what we have here is actually an inverter. That's where we're going to attach the harmonic library. This could be a VFD drive attached to any of these motors, for example. The procedure is in essence the same. We're going to go over to the library pull-down menu and then select harmonic, and then what I'll do is I'll just create a new manufacturer. Actually, what I'm going to do is click on add. The manufacturer will be inverter, for example. Okay, and the model will be solar PV inverter, for example. Under the reference, you could put the data sheet. This is going to be a current source. You can put datasheet information there if you like, and then once it's created, you're going to go edit. First, let's start from the top and then work our way down to the bottom. The fundamental frequency is going to be 60 Hertz. This is going to be a 6 pulse, and if we select populate harmonic spectrum, we see that it has the orders that are part of a typical 6 pulse. So you have your 5th, 7th, 11th, 13th. And for the 5th, and I don't want to go back and forth, to the PowerPoint, but I'll just fill it out here in front of you. For the 5th, it is actually a percentage of the fundamental current. So we're going to put here 20% magnitude. For the 7th, order is going to be 14.3. percent magnitude. For the 11th order, it's going to be 9.1, and again, I'm getting this just from the that data sheet that I showed you in the last slide. 7.7. Okay. The fundamental current, as I mentioned, was 600 amps, and then ETAP automatically fills out the magnitude in amps right here. You can also fill out the magnitude in amps, and ETAP would provide you with the magnitude in percent. Over on the right hand side, you can see a representation of the voltage waveform on top and the current source on the bottom. We're going to click OK to save this harmonic source. Click on close. So that's now part of your library. You can continue using that for any project in the future. That's going to stay in your master library. I open up the source, in this case the inverter. I go over to the harmonics tab, and then I'm going to select it from here. I think the manufacturer I put was inverter. There it is, solar PV inverter. Click OK, and then the same waveform and spectrum actually appears, I will select OK. So the next thing I like to do, and this is how you will set up most of your projects. It's really simple, really. The rule book already contains, right, the limits for the point of common coupling. For example, in this case, is going to be total harmonic distortion of 5% and total current distortion of 3%. So that's automatically going to be a global setting. The next thing is I'm going to switch over to the harmonic analysis mode from the toolbar here, and this is to let ETAP know, okay, I switch from load flow or short circuit or protection and coordination to harmonic analysis, and I will open this study case. And this study case is very important because this will allow you to select which buses you want to display on the results for the plots, and as well as what you want reported on the one-line diagram. So it's just basically for the plots and the single line diagram reports. This is where you can control what kind of information you want to display on the single line diagram or on the plots, because what happens is if you have everything selected by default, it may get crowded on the single line diagram. So this way, I want to focus on these three locations: my main bus, which is the point of common coupling or PCC. I want to focus on bus number 1 and bus number 2, which is over on the DC composite network right here on the line side of the inverter. So that's where I want to focus. I'd also like to see, for example, cable 14, the branch. If you want to see like total branch or total current distortion through branches, I would select, for example, your branches, which could be cables or transmission line or transformers, and select those elements. So after you have selected those elements, select OK here, and then I will go ahead and run a harmonic analysis study. And the first thing that you see on the screen is very important, of course, is the total harmonic distortion, right, at each of the buses that I have selected. So main bus, sub 3, bus 1, and bus 2 over on the left hand side. The alerts, it's down here. The alerts will in essence give you an idea if, for example, your point of common coupling, your PCC, has exceeded the limits, right? In this case, my main bus is okay. So if we were to interconnect with the utility and they ask for a study for the harmonic analysis, we could provide them this. We could say yes, we're well below the limit. We're actually under 1%. But if you take a look at the alert view, we actually do have some issues at one of the locations, which is bus number 1. We have a limit of 1.5, but we're operating well above that. In fact, if you take a look at the harmonic order slider right here, my total harmonic distortion at bus number 1 is greater than 7.29 percent. So that's something that we need to correct. So what I have here is just a text, and I'm going to say correct 7.29% total harmonic distortion. Just a note, so I don't miss it. Now, the harmonic order slider. Going back to the slider. This is a very useful tool in the sense that as you start to scroll to the right, you've got the fundamental frequency here. So you basically have your load flow, your steady state load flow results. And then as you begin to scroll down over to the right, you now have your 5th, you have your 7th, 11th, 13th, and so on. Depending on the study case, you could specify how far you want to go. Now, because this happens to be a 6 pulse, as you could tell, we have actually predominant harmonic content on the 5th right here. My amps on the 5th order is actually 179.5 amps, 124 amps on the 7th, and 71.6 amps on the 11th. So they just begin to decrease after that. So what I like to do is actually want to make a note, because when I begin to tuning my filter, I want to know what's the harmonic order that contains the highest content. So in this case, I go ahead and open my my notepad here. Maybe let me decrease the size of the font here a little bit, and I'm going to put here fifth order at 179.5 amps. Click OK. There it is. Those are just my notes. I continue to have my notes. The other useful feature available in the software would be the ability to open a plot and see, for example, the waveform for bus 1 in this case. So if you wanted to display the waveform, time versus voltage here, right, in cycles, you can see the combined fundamental with the 5th, the 7th, 11th, 13th. So this is kind of how it would look on the measuring equipment, if you would. Okay, now that I've recorded some of the harmonic results there on the one-line diagram, you can certainly also check, print the report and have all the information at your fingertips. So if I open the report again from the right-hand side, I go over to results, and I want to output the report in PDF format, right? You could see here the complete report, not just for the location bus 1, but for every single location. You basically have your fundamental column right here, and you have your total harmonic distortion, right, and the various indices. Very important is the ability to quickly see when a location has alerts. And that's what the hashtag and the star basically mean here for bus number 1. It just basically means that we have exceeded. And as part of the report, you also have an alerts portion. It's a very comprehensive report. Unfortunately, we don't have the time to go over it, but this is in essence the report you would see at the end as an appendix to a harmonics study. Okay, now moving forward with the example, what I like to do now is quickly display the following information. So I would like to display on the right-hand side, I have my harmonic analysis view, and I'm displaying I've switched the harmonic order slider, so it's showing the total harmonic distortion here. And then I'll close the DC system, because what I like to do is I want to open my load flow view. Here's my load flow view, and at the moment I have data blocks enabled. I could turn them off here. And as you know, as part of the three-dimensional database in ETAP, you could have multiple one-line diagrams representing the same single-line diagram, right? You could just have multiple ways of representing the data. So that's exactly what I did. It's just I have a copy of the same one-line diagram on the left-hand side. What I like to do is just display, for example, power flow information. You have, the standard ETAP results, but you also have the ability of displaying the results as data blocks. Data blocks allows you to customize the information. For example, I'm using on this data block, besides the ID, the nominal voltage, and the voltage drop as a percentage of the nominal voltage here, I'm also displaying my loading real power, reactive, as well as my power flow in amps, right, going through this particular point or bus. Also, I have power factor displayed on the left hand side as my load flow results. And what I like to emphasize here is that on the left hand side, this is typically the load flow analysis that you would use to be sizing your protected device frame, your cables, your transformer, and you're not taking into account harmonics, obviously. But once you perform, attach a harmonic source to the system, and you display the actual harmonics content, and you express it as the total harmonic distortion, you could see that on the line side of this 1.5 MVA transformer, after you attach harmonic sources for the inverter or the VFD drive, whatever that may be, you actually have a higher amps, total amps at 110 versus 106.9 amps, right? So if this protective device here was set to pick up at 108 amps, right? It wouldn't trip under normal conditions or without any harmonics. But over on the right hand side, once you attach the harmonic source and the system is operating using the that harmonic source current harmonic source, you now see a current being drawn of 110 amps. So if that circuit breaker again was set to 108 as the pickup or the trip, you would pretty much have a nuisance trip, right? So that's just a quick way to see why it's so important to take harmonics into account and how it could cause problems with not just your cables but also your protective devices and transformers, as well as shortening the life of some of your equipment. Okay, so moving on to this exercise, what I like to do here now is I would like to size a filter now. That's in essence what I like to do. So over on the left hand side, actually I guess on the right hand side, I could do it either way. I'm gonna switch over to edit mode. Okay, and on edit mode, what I like to do is I would like to put a harmonic filter here. There's a filter right there. I will attach it to my one-line diagram. You notice that when I attach it on the right-hand side, it automatically appears also on the left. And the reason why is because we're using the same database. All we're doing is having the ability to display the data, different data on the same single-line diagram. Okay, and then the other item I like to introduce here is just a circuit breaker. And the reason why is because under normal condition, you notice up here my configuration, under normal condition, this actually should be set to open, because I haven't actually commissioned this particular filter. It's not found in the field. At this point, all we're doing is a study. And when I switch from normal to on, as you could see, then the filter becomes on. Same thing on this side. It's on. Now it's on the normal. Okay. Now, to begin sizing of this filter, what I'm going to do here is, so there's my power flow over on the left. I need to open my filter here, go over to the parameters. This is going to be a single tune. My rated kV here is not 480. This should be the single phase cap rating. So it's 480 or 0.48 kV divided by square root of 3. So that's going to be 0.277 kV. Okay, I'm going to use a Q factor of, I'll just leave the default. Max kV, this would be the three-phase rating, so it's 480, right? And then to begin the sizing the filter, we're going to click on Size Filter here. And we mentioned that I'm trying to correct basically the fifth, right, or the highest content, which are in my notes over on the right hand side. So I'm going to say harmonic order fifth, harmonic current, it's 179.5 amps. Over on the right hand side, you have sizing options. You got power factor correction, minimize initial cost, or size per minimized operating cost. This is mainly more so for utility or distribution type of users. For industrial, we typically go with power factor correction. So we're going to jump right into the power factor correction option here. We're going to select existing power factor, right? And my existing power factor is actually before the filter is put in place. It's on the left hand side. You could see here is 86.74. Okay, and of course the desired power factor is going to be unity or 100%. And then my load MVA, again going over the results, my loading MVA was 754 MVA. This is basically how much is being drawn here. Because this is going to be single phase load MVA, I just need to divide it by 3, so this is going to be 0.754. We're going to click on Size Filter. Okay, and then the results here are grayed out because they're ready to be, you click on Substitute, and they're ready to be placed here on the on the harmonic filter editor. I guess the last thing I need to specify is going to be my inductor maximum current, and I can specify that here. This is 1200 amp maximum current. I'm going to click OK here. All right. And now just to show the before and after, I could do it over on the right hand side. Yeah, I could do it on the right hand side. Yep. So I got my load flow on the left and my harmonic analysis on the right hand side. In order to run this, I would like to bring my filter online. There it is. Run harmonics analysis. Okay. And you notice the total harmonic distortion has now dropped from 7.29% down to 2.2% total harmonic distortion. Okay. The last piece of information I like to go over is running the frequency scan. It's over on the right hand side. I select run frequency scan. I open my plots. I look at my waveform for bus number 1. Click collect. Okay, that was a waveform. Now if I want to look at my spectrum, there it is. Okay. And if I want to look at my as a frequency scan, there it is. So in essence, what we have is the harmonic order on the x-axis here versus the impedance. This makes it very easy to see the various resonance, and also allowing you to better tune a filter. With this, I like to say thank you for watching this presentation.